Hello, welcome to our class, Heterogeneous Computing. Today, I'm going to introduce OpenCL device architectures. We're going to begin with the introduction of process architectures. We're going to discuss the trade-offs in hardware design and some of the important and very interesting features in modern microprocessors. Then we're going to look at some of the representative CPU architectures and the GPU architectures. Following that, we will talk about FPGA architecture and briefly introduce how OpenCL is mapped into FPGAs. OpenCL has been proposed about 8 years ago and by a group of industry partners. OpenCL has been shaped by many of these vendors from the beginning because the vendors are having different products. So the goals of target of features from OpenCL may vary from device vendors to another. However, OpenCL allows detection of hardware capabilities. So the unique features from these vendors can be explored by OpenCL platforms and also in applications implemented using OpenCL. OpenCL has a relaxed consistency model. It's block-based parallelism, which can run on different process architectures, including symmetric multiprocess architecture (SMP), or multi-threaded architectures, or SIMD or vector processors. OpenCL is platform independent, so OpenCL applications can be ported into multiple platforms. However, performance still depends on the algorithm and how well it can be mapped to the hardware architecture that it runs on. There have been processors with different features. For example, cores. The definition of cores varies a lot. We have Superscalar core, SIMD core, VLIW core, very long instruction word core. Different cores have different performance on integer and floating point computing. Different processors may have different number of cores, so we call them multi-core or many-core. For these core-based processors, from software point of view, it might be difficult to keep the cores busy all the time. As a result, there are a kind of processors called multi-threading or multi-threaded processors, which allows the programmer to increase the amount of useful work available to occupied compute resources. Also, in these modern processors, cache and memory hierarchy plays an important role in affecting or improving the system performance. More and more people are putting heterogeneous processor components. More and more people have seen heterogeneity in process architecture in the form of big core and small cores in the same chip, or CPU and GPU on the same chip, or even CPUs and FPGAs on the same chip. There are other design limitations that will affect the architecture and the implementation of microprocessors. For example, frequency, power consumption, energy efficiency. Conventional CPU processor, conventional CPUs are optimized to minimize the latency of a single thread. So the goal is to efficiently handle control flow of intensive workloads. There are a lot of chip space designed, there's a lot of space on the chip devoted to caching and control logic, and multi-level caches are often used to avoid long latency. These chips typically have limited number of registers due to smaller number of active threads that will be running on this chip. And the control logic are devoted to reorder execution provide instruction level parallelism, and minimize pipeline stalls. Superscalar execution is a very interesting, Superscalar execution is one of the important features in modern microprocessors. In CPUs of superscalar process architecture, they maintain the dependency of information between instructions. Now keep in mind, this kind of dependency information is maintained in hardware so that the software developers, they have no idea or they don't care about the hardware implementation. In processors with superscalar execution, the dependency information among instructions are maintained in hardware. As a result, the software developer's life is made easier. So programmers don't have to worry about how these instructions are actually scheduled on the process hardware architecture. The compiler, the CPU hardware will extract parallelism from code automatically without the involvement of programmers or compilers. For example, let's look at the example on the right. So we have a program that consists of an instruction stream A, where I have 6 instructions, where I have the instruction stream A has 5 instructions. And the first instruction is add A, B, C, which means that we're going to add the 2 operands, B and C, put the addition or sum of these 2 numbers into register A. Similarly, we have multiply instructions and a floating point multiply instructions at the end. So the processor will generally have instruction fetch stage, instruction decode stage. During the instruction decode stage, lots of activities going on. During the instruction decode stage, there are a lot of activities will be performed by the microprocessor. It will look at the operands. The processor will look at the operands and determine the dependencies among these instructions. For example, the first instruction, the result is stored in register A, which is read in instructions ADD During the instruction decode stage, there are a lot of activities going on for the microprocessor to analyze these dependent. During the instruction decode stage, there are a lot of activities going on for the microprocessor to analyze these instructions, in particular their dependencies. In this example, because the way we use these registers, this multiply instruction depends on the addition instruction, because the result from the addition instruction is stored in register A, which is read by this multiply instruction. Similarly, we have dependencies on instruction multiply and with this addition, because we're reading results of D and use that as one of the operands for this addition. So all these dependency information will be analyzed and it will be maintained by the microprocessor in its control logic. By the time these instructions are issued into this pipeline, these dependencies will be enforced. In this processor example, we have 2 integer ALU unit and 1 floating point ALU, which means that at any given time we can execute 2 integer instructions along with 1 floating point instruction simultaneously. And because of the dependency among these instructions, in this example, we are able to schedule this addition instruction and this multiply instruction as the first batch or the first cycle, followed by multiply and this add instruction as the second batch. And because of the dependency, the third instruction, the final instruction, floating point multiply, will be executed in the third batch. So in this kind of instruction scheduling, we can see that the performance is greatly improved over the serial execution. Yet, on the microprocessor, we need to devote a large amount of chip area to implement such control logic. To further improve the performance, people have been using so-called speculative instruction execution, which can expand the out-of-order execution window so that as many instructions can To further improve the performance, some microprocessors even employ so-called speculative instruction execution, which expands the instruction window further. With speculative instruction execution, the instructions beyond the basic block or beyond the branch instructions can be possibly executed if there's resource available on the data path. But some of these instructions may have to be squashed if, for example, the branch instruction turns to be taken the other direction. So there will be some work will be squashed. So there will be cases the unnecessary work will be squashed. Hence, these CPU cycles will be wasted. Another interesting processor feature is so-called very long instruction word, or VLIW. So from the name, you know that we're going to have instructions that consist of very long. From the name, you know that these instructions consist of multiple operations and multiple operands. And the processors with very long instruction word will depend heavily on compilers because the compilers have the responsibility to generate these long instruction word by analyzing the source code. Let's look at this example. So we have an instruction stream. We already have the compiler. We're taking the same example from the previous slide. We know that we have several instructions streams. We know that we have possibly 3 batches of instructions that can be executed. So the instruction stream is illustrated in this green box here. We have first batch addition, Another very interesting processor feature is called very long instruction word. Let's look at the example on the right. We're now looking at the same instruction stream that coming from the previous slide. And we know from earlier discussion that these 5 instructions can be organized in 3 batches or 3 cycles to make it simple. The first 2 instructions, addition and multiply, can be executed at the same time and then followed by another multiply and an addition. In the third batch or in the third cycle, That's the final instruction, floating point multiply. So these instruction streams go through the same instruction fetch stage, while at the decoding stage, these instructions will be decoded. But keep in mind, at this case, because we're using very long instruction word, there's really no need for the hardware to maintain a very complex logic to analyze the dependencies, because we assume all these dependencies have been resolved at the compilation stage. And then the scheduling of these 3 batches of instructions will become very simple. We just schedule these 3 batches one after another. So all these instructions that are executed together, they are in fact embedded in the same very long instruction word. In this example, what we show here is, even though the hardware implementation might be simple compared to the superscalar in terms of the control logic, we have the processor depends heavily on the compiler support. All these very long instruction words have to be implemented, or all these very long instruction words have to be filled out by the compiler at the compilation stage. Each issued instruction can be then, after that, each issued instruction is a long instruction word comprising multiple instructions to be issued in parallel. And that is how the VLIW instructions are mapped into processor pipeline. SIMD and vector processing. SIMD represents single instruction multiple data. SIMD processors directly allow the hardware instructions to target parallel execution. This is very useful for vector operations, and even for operations that apply on a very large array. Well, looking at this example here on the right, the instruction stream is similar to what we saw from the previous 2 slides. However, the major difference is that all these instructions are now vector instructions. So the ADD is now ADD.V, and the operands A, B, and C are in fact vector operands. So it's not a single word or a single byte. It now becomes an array of words or bytes. The instruction streams will go through the instruction fetch and decoding stage. At decoding stage, the dependencies among these instructions will be analyzed. When these instructions are scheduled, they will be mapped or issued into these multiple. They will be issued to the. When these instructions are scheduled, they will be issued onto those multiple ALUs for integers and for floating point to accomplish these single instruction for multiple data operations. SIMD basically encapsulates a request that the same operation applies on multiple data elements. As we can see from this example, the scheduling and the decoding logic can be made simple because the same instructions are applied to multiple data, and the dependencies among these instructions are mostly analyzed at compilation time. Similar to SIMD, vector computation works on very long vectors. Implementation-wise, vector computation is often implemented as a pipeline, and it supports gather, read, and scatter write operations. As we see from the previous slide, the SIMD simplifies scheduling and decoding logic as it performs multiple operations using a single instruction. There are certain trade-offs in this design. It is not really beneficial for code without significant data parallelism, and it's challenging for the compiler to extract data parallelism if there's no bit. It's challenging for the compiler to extract data parallelism for and the vectorization of loops has little success except very simple cases. In reality, in the commercial processors available, vector processors are often used in supercomputers, whereas SIMD is more common in these desktop and server processors where the CPUs can have extensions of vector instructions. Hardware multithreading, also known as hyperthreading in some of the Intel's microprocessors. Hardware multithreading takes a different approach as the SIMD. It tries to exploit thread parallelism. By thread, we're really talking about software thread, in the sense that these threads or these instruction streams can run simultaneously. Let's look at the example on the right. We have two instruction streams, A and B, and we can think about these as different threads. And we color code these instructions blue and red to make it clear in this illustration. These two instruction streams, they are independent to each other. Well, in this example, these two instruction streams are independent from each other. In a software implementation, we can, from the programmer's perspective, these two can be two different threads or two different processes. And these two instruction streams will go through instruction fetch and decoding stage. The instruction dependencies within these streams will be analyzed by the hardware. As we can see here, there are dependencies between these addition instructions and multiplying instructions in stream A. Also, there are dependencies on those floating point addition and multiplying instructions in instruction stream B. And because these two streams are independent, the instructions that belong to these two streams are independent, which means that we can possibly execute these two instructions or multiple instructions from two different streams if there's resource available. As a result, to schedule these 10 instructions from two independent streams, we now have a schedule like this. In the very first batch, we have two instructions that are coming from stream A, and these two instructions are independent. That's why they can be executed at the same time on two different integer ALU units. The first instruction from instruction stream B is a floating point instruction, and because these instructions are independent from any of the instructions in instruction A, so it can be executed on the floating point ALU at the same time as those two instructions are executed on integer ALUs. So as we can see, it is quite useful for large machines and even single CPUs to run multiple tasks which are independent in nature. And it is trivial to extract instruction parallelism from two or more independent threads because there's really no dependencies. But this comes with a cost. In the processor hardware, we need to have extra registers, even extra cache, to manage and schedule multiple instruction streams. Because while you are executing these instructions, and because they are from different threads, their states have to be maintained separately. Another example is so-called time-sliced thread scheduling. In time-slot thread scheduling, the goal is to make sure that the pipeline or the ALU is kept busy. And to do that, in this kind of processor, threads will take turn to occupy the process data path in a round-robin fashion. On the right, we have, again, two instruction streams, A and B. And we know that these instruction streams are independent. And so we'll put these two instruction streams through the instruction fetch and decoding stage. And in the scheduling, we actually have a very simple task. We just alternatively take one instruction from one of the streams, and then in the next cycle, we'll execute the first instruction available in the other stream, and so on. So what you see here is black and white, so what you see here is black, red, representing these instructions are executed in a round-robin fashion from these two different streams. The major advantage of this time-sliced thread scheduling is to hide latency. The pipeline latency can be covered by scheduling more threads. Also, it can reduce the cost in the forwarding logic because we don't have to maintain a very complex forwarding logic in the superscalar architecture, because we don't have to maintain a complex forwarding logic as we do in the superscalar architecture. And most importantly, because these threads will possibly access memory, and we know memory gives you long latency, and to reduce such thread stalls due to the cache misses, or because of the branches, we can change the order of thread execution. So let's say if a thread is trying to do memory access and there's a cache miss. While this thread is waiting for the data to come back from the memory subsystem, the other thread can be scheduled onto the data path so that the processor data path is kept busy. Now, in the same direction, people have been using these hardware multithreading or time-sliced multithreading to achieve so-called throughput-oriented computing. In throughput-oriented computing, essentially, the system will take as many threads as possible to keep the processor busy. In our example here, we are having 7 threads, and each thread takes some computation operation and the memory operation. Now, because memory operation takes a substantial time, so it's beneficial for the other thread to be scheduled onto the processor to keep the data path busy. As a result, what you see here is these threads from 0 to 6 take turns to be executed, and while the other thread is executing, thread 0 is actually completing. Thread 0 is trying to complete the memory operation. If you look at a single thread, what you see here is it only gets a fraction of the time to occupy the CPU. But because of the memory latency that we need to hide, it's actually beneficial for the overall throughput performance. So even though a single thread's performance may be slowed down, but overall, the throughput of the system is improved. Multicore architecture. It is not surprising that chip vendors produce processors with multiple cores for throughput-oriented computing. These cores execute independently. If they need to share data, they share through cache or memory. As we see in these two pictures down below, we have a single core processor on the left, and we have a dual core processor on the right. As you can see, the dual core processors, each core has its own pipeline and also a private level 1 data cache. They too share a layer 2 data cache, and they can then exchange data through the layer 2 data cache, also through the main memory. For this to work properly, there has to be cache coherence protocols so that the operations to the shared data can be synchronized across these multiple cores. System on chip. It's very common, especially in embedded domain, that the processors includes multiple units on the chip for the purpose of low power and low cost. We have one example here. This is a TI processor, Cetera AM335X. It's a very widely used embedded microprocessor. On this chip, it has an ARM Cortex-A9 core. Along with it, there is a 3D graphics processing unit. Also, you can see that there are many other interesting on-chip units built into this processor for different purposes. For example, there is an on-chip quad-core programmable real-time unit for real-time processing. It has a vector floating unit. It has a vector floating point computation unit. Also, in terms of interfaces, this chip has multiple interfaces to the external system. For example, 2 parallel camera ports, a dual port, 1 gigabit Ethernet, LCD controllers, etc. USB ports, SD card interface, GPIOs, etc. Cache hierarchies and memory systems. Hierarchical cache and memory architecture has been used with processors for quite a while. As we can see in this diagram, there are small amount of storage spaces on the processor, including registers and level 1 cache. Off the chip, we have level 2 cache, which in the modern processor case, level 2 cache is also within the processor. And we could have level 3 cache and then main memory, and eventually secondary memory, which is essentially the storage disks and other permanent storage components. The cache hierarchy and memory subsystems are organized in such a way is mainly because the trade-offs between speed, size, cost. As we're getting close to the chip, the speed is faster, however the size is limited, and also the cost is high. As we go further away from the processor, the cost is very cheap, however the speed gets much slower. So why will this kind of cache hierarchy plus memory subsystems work best for the processors? It's mainly because cache locality. Cache locality, basically it says that the opportunity or the possibility we can access the same data is quite high. And if you look at this top diagram, if the y-axis represents the probability of reference, x-axis represents the address space. If you study all the applications software that often run on these processors, you can typically see the axis clustered in certain address range. And also, this locality can be categorized into 2 aspects, temporal and spatial. Temporal locality is really the locality in time, which means that the most recently accessed data will be accessed again in the near future. That is why it makes sense to keep most recently accessed data items closer to the processor. Spatial locality, that's the locality in space. This spatial locality refers to the fact that if you access a data item, it's highly likely that you will access a data item that is next or close by to the current one you are accessing. Therefore, it makes sense to move blocks consist of contiguous words to the upper levels, with the hope that the nearby words or double words will be accessed in the near future. Combining the temporal locality and spatial locality, the cache and also the memory hierarchy together will help the processor improve its performance. In the next few slides, we're going to look at the architectural design space for different processors. We'd like to use this picture to show the architectural trade-offs in different processor designs. As we can see from these 4-5 different kinds of processors, the numbers of cores are quite different. Some has 6 cores, some has 8 cores, some has 24 cores, and so on. Also, if we look at the cores, they're quite different as well. The numbers and types of pipeline are so different that you can't equal one core in one processor with the other core in the other processor. For example, in AMD Radeon HD 6970 processor, this is actually a GPU. It has 24 cores, and each core supports 1 through 248 64-byte state per core, and also each core has 16-byte SIMD that supports long vector instructions. Accelerated Processing Unit, or APU. This term is given to processors typically has general purpose cores and also an application-specific processing unit, often the GPU. In this example, AMD E350, codename Zacate, it has low power cores. In fact, it has 2 low power cores on the chip, and the GPU cores supports SIMD, and the x86 low power cores and GPU cores share data memory, DD3 off chip, but they have private level 2 caches independently. But the low power cores and GPUs, they each has its own private level 1 and level 2 cache. On chip, these cores are connected through shared bus and memory controllers. This is an APU-like processor from Intel. This is Intel Sandy Bridge processor family. It has several general purpose cores. In our example, 4 cores, and it has an embedded graphics processor on chip. And the general purpose cores and embedded GPUs are sharing this level 3 cache. In the next couple of slides, we're going to talk about modern GPU architectures. GPUs are very famous for its massive parallel processing units on the chip. Most of the GPUs have an array of independent cores called compute units, and different vendors may have different names for these compute units. Some are called stream multiprocessors, like in NVIDIA. These processors have very high bandwidth on chip, and they have banked L2 caches and with high-speed connections to main memory, and specifically the graphics memory. Banks of the memory allows multiple access to occur in parallel, which can reach up to hundreds of gigabytes per second. And these memory and caches are different from the memory and caches in general purpose processors. The memories and caches here are non-coherent, which makes the processor design simpler, also improves the degrees of parallelism in those parallel processing units. Most of the compute units on GPUs are based on SIMD, single instruction multiple data architecture. And both AMD and NVIDIA have 16-byte SIMDs. Also, for these SIMD processor cores, they support hardware threads, but the way to map these threads to the processor units and the number of threads can be mapped can be different from vendor to vendor. On the processors, there are a large number of registers that are used for fast context switching. Because we're talking about hardware multi-threading, then each thread needs to maintain their states, and large number of register files will with large number of register files, there's no need to save or restoring states. And also the data is persistent across thread execution. Both of these GPU vendors, they have a combination of level 1 cache and a user-managed scratchpad. These are all on-chip memories that can be accessed by the processing units. In AMD, the scratchpad is also called local data share, and in NVIDIA it's called shared memory. Scratchpad is heavily banked and supports very high bandwidth, usually in the order of terabytes per second. In the context of OpenCL, there are work items that are being computed by the processing units. Here, work items are automatically grouped into hardware threads called wavefronts or warps on the GPUs. On these GPUs, on each of the SIMD cores, there is a single instruction stream being executed. And because it is SIMD, there are multiple SIMD lanes that are currently executing the single instruction. So in theory, you can have up to 64 work items into a wavefront in AMD processors and 32 in a warp on NVIDIA processors. These are basically the active number of hardware threads that are currently executing the instruction. For the case of when the program has control flow that has branches, for the case of the program has branches in the control flow, the processor will be able to mask some of the SIMD lanes so that the operations will not be applied on a certain subset of the dataset. NVIDIA has the term called single instruction multiple threads, which essentially explains the multiple threads that share the instruction stream, and these multiple threads are being concurrently executed on these SIMD cores. And each of the work items has its own program counter, and they execute in lockstep on such a hardware. But still, because of these multi-threaded support in the processor, so that's why multiple software threads that can be executed in parallel. For divergence, for example, the branches in the software program, and these will be handled by using mask or predication. And as a result, the performance is dependent on the work items mapped to this SIMD architecture. As you can imagine that if you have a large enough branches, then this will greatly reduce the performance because a portion of these hardware multi-threads will be wasted. Here we want to illustrate the memory model in OpenCL, although it says AMD, but this applies to other graphics processors. We're talking about several types of memory: global memory, constant memory, local memory, and private memory. Global memory is the lowest level of memory hierarchy. It maps to the cache hierarchy, and in the context of GPUs, we're talking about the graphics memory on the graphics card. That's the video card's main memory. And that's furthest away from the processor. Constant memory is often part of the global memory space, but the constant memory is optimized so that it stores the values that will not change at runtime. So it's used for scalar units rates, for example, reading constant from the memory. Local memory is where the processing elements or computing units shares across multiple processing elements within a computer unit. And this maps to local data share, such as in AMD, or the shared memory on the NVIDIA architecture. We can use local memory to share data between work items of a work group. And local memory is on chip, so it has very high memory bandwidth that can be accessed from the SIMD cores. Private memory is even closer to the core. It usually refers to the registers or scratchpad. We see here a AMD GPU architecture, and also we want to show how the OpenCL memory are mapped to such a GPU architecture. On the left, it illustrates what's inside this AMD GPU. The command processor element and also ultra-threaded dispatcher are responsible for programming the compute units and also scheduling the threads. We have, in this case, 40-some compute units. Each compute unit has its own level 1 cache. Through the level 1 cache, the compute unit is connected to a shared level 2 cache through a crossbar interconnect. Through level 2 cache, there are 8 memory controllers which connects to a global shared graphics DDR5 memory. So with this DDR memory, level 2 cache and level 1 cache, you have a complete memory address space. And this is going to be used for the global memory in OpenCL. If you look into the details of a compute unit, what we see here is inside a compute unit, it has 4 SIMD cores. And these 4 SIMD cores share a local memory called local data share. This is in fact the local memory of OpenCL. And if you look even further into this processor core, within a SIMD core, it has 16 SIMD lanes. And each lane can perform operations on vectors of registers. These vector registers are what we consider private memory in an OpenCL context. Now, with a good understanding of the GPU architecture, let's look at how we should design an OpenCL kernel so that we can take advantage of the GPU performance. An ideal OpenCL kernel for a GPU would have thousands of independent pieces of work. Because we have massive amount of SIMD cores, multi-threaded cores available within these compute units, so it's going to be beneficial for us to have thousands of independent pieces of work which can be scheduled onto these processing elements within compute units. Also, the context switching available from these cores can allow the kernel to hide latency while doing computation on these massive amount of data. Also, the cores should be amenable to instruction stream sharing. We said earlier that the divergence of program execution path may potentially cause waste of CPU cycles in these SIMD cores. So we should really try hard to prevent divergence between work items. We would like to have the work items to be performed on the same operations as much as possible. Also, for OpenCL core, we would like it to have high arithmetic intensity. The ratio of math operations to memory access is high. That will be beneficial for the cores to keep itself busy. And because the memory bandwidth available to GPUs are generally very high, so it's not going to be limited by the memory bottlenecks. Next, we're going to talk about FPGA device architecture and OpenCL for FPGAs. Some of the slides are taken from Intel Altera tutorial on OpenCL for FPGAs, which was offered at ISCA 2016 conference. Programmable logics have been used in many different aspects. Programmable logics have been used in many places, such as consumer electronics devices, automobiles, test instruments, communication devices, military applications, and general computing. So it makes sense to study how the FPGA architecture is unique and also how OpenCL can be applied onto FPGA devices. The basic elements inside FPGA logic. There are several different logic blocks inside an FPGA device. Essentially, FPGA logic is made up of logic elements. And in some cases, for example, Altera, they call this adaptive logic modules, or ALMs. ALMs can be implemented into arbitrary functions. Let's look at the diagram of ALM. In an ALM, typically there's a combination logic with up to 8 inputs, and the output of the combination logic can be fed into 2 adders, which again, these outputs of the adders can be fed into registers to implement state machines. And the uniqueness of this ARM is that the combinational logic can be arbitrarily divided into LUTs or lookup tables of different number of inputs. For example, we can use this ARM to implement a 6-input LUT or 2 4-input LUTs, or even 5-input LUT plus a 3-input LUT. So this creates a lot of flexibility on implementing the functions. LUT refers to lookup table. Lookup tables are the ones that implementing combinational functions by using programmable table, or in fact they are using multiplexers to implement such functions. In this example here, we are trying to implement a function x which has 4 inputs a, b, c, d, and the exact function is defined in this formula here. The way to implement such function in FPGA is to use such multiple levels of multiplexers. At the bottom, these are the programmable bits that we can write into EEPROM or SRAM, and these bits will actually be selected by using a combination of A, B, C, and D. Now, by working through the logic design, you can figure out what exact number, either 1 or 0, have to be put into this programmable bits. With logic elements and adaptive logic modules, to build a larger function, we need a large number of LEs or adaptive logic modules. So this is the logic array block, which contains of groups of logic elements. And we typically arrange these LABs in an array. So we can program these arrays so that they will be connected to other adjacent LABs to implement certain function. We can connect these LABs through the column or row interconnect. And these interconnects may span all or parts of the array. As we see here, we have an array of LABs, and we have row connectors and column connectors so that we can connect these logic array blocks as needed. FPGA routing. There are many resources on an FPGA chip: LABs, logic elements, adaptive logic modules, and to implement certain functions, you need to connect these different resources. All the device resources can be fed into or be fed by routing in the device. Routing is basically connecting these logic elements from input to output and chain them together. And we can adjust the length of this routing to make sure the timing requirements are met. Routing scales linearly as density increases the local interconnect. The way to understand this is that you have logic elements or adaptive logic modules within a logic array block. You can connect them as needed. Also, you can connect components across logic array blocks or adjacent logic blocks. You can even run through longer routing through the row interconnect or column interconnect to span to a larger number of LABs or even the entire device. FPGAs have embedded memory components on the chip. Memory, we call them memory blocks. Memory blocks often create on-chip memory structures so that we can use such structure to store temporary variables and data. We can configure single port or dual port RAMs, or read-only memory, or FIFO buffers, depends on the application needs. And we can even initialize the RAM or ROM contents on power on of the device. The typical sizes of these memory blocks is 20 kilobits, and one memory LABs is about 64 640 bits. And of course, you can build larger memory through banks of such memory blocks. Digital signal processing blocks, or DSP, have been used in FPGAs. They are quite useful for signal processing functions, such as FFT transform and multiplier accumulation, and they are dedicated units that can be programmed together with other logic elements to implement certain functions. For example, in one of the latest FPGA family, Intel Altera Area 10, Area 10 has DSP blocks that can do 32-bit IEEE compliant floating point multiply operations. And as we said earlier, such DSP is powerful and can be chained into your other logic elements or other logic array blocks to implement larger product operations. FPGA I/Os. In order for the FPGA chip to talk to external devices, it has to have I/O elements. The I/O elements on FPGAs are advanced programmable logic blocks that can connect directly to row or column interconnect. For these I/O elements, it can control I/O features such as is it input, output, or bidirectional, or is it going to be using differential signaling, or the internal termination or pull-up resistors. High-speed transceivers on FPGAs are advanced I/O elements that are used for existing high-speed protocols such as USB, Ethernet, PCI Express, etc. The high-speed transceivers are important for connecting to other existing interfaces. FPGA clocking structure. FPGAs rely on dedicated input clock. Internally, you can use the input clock to generate other clock frequencies using PLL or DLLs. Inside FPGA, there is a clock control block will determine the power down and power up, and also other states for power savings. Also, it can select clock signals to feed the clock routing network. The clock control block can also be used to feed clock signals to different parts of the FPGA components. Clock routing network is a routing channel that's reserved for driving clock signals. You can use a global clock network to feed the entire device. You can also have hierarchical networks to feed certain device areas. PLL, phase-locked loop, is also a very popular design to change the frequency of input clock so that it can generate different frequencies or different phases based on the needs of the logic. In this example, this is a PLL module instantiated inside the FPGA. The input clock signal is a 100 MHz signal, and through the PLL, we can generate 3 signals. In this example, we can have another 100 MHz clock signal generated, or we can increase the frequency from 100 MHz to 200 MHz by changing the ratio to 2:1. On top of that, we can even change the phase, so we can generate a 200 MHz clock with 90 phase shift compared to the original input clock signal. To program FPGA, we need to use SRAM technology to configure the interconnect, also the LUT functions. And because most FPGAs use SRAM technology, so it's volatile, which means that it must be reprogrammed at power on. In order to program the FPGA, the configuration information must be stored somewhere that can be accessed at the power on stage. One can use external EEPROM, CPLD, or even CPUs to program the FPGA chip. There can be classified as two different programming methods, including active and passive. In the active programming methods, the FPGA controls the programming sequence, whereas in passive mode, a third-party processor, typically a CPU, will control the programming. We can also program the FPGA through JTAG connections. This picture illustrates the important components inside an FPGA, including the logic blocks or logic elements, the interconnects, and also the DSP blocks. It also shows the transceivers and other I/O elements that are important to talk to other internal or external components. Here is an example of FPGA chip. It's a very recent one from Intel Altera. It's Area 10 GX1150, which has over 1 million logic elements, including 1.7 million registers and over 1 million 4-input LUTs. It has total about 54,000 memory blocks, and each block has 20K bits. It contains 1,500 DSP blocks, and it has 32 very high-speed transceivers and 2 hardcore PCIe blocks. FPGA is being widely used in many applications because it has a number of unique advantages. The chip density is high, and also the chip is very flexible. So the users can create many complex logic functions, and these functions can be integrated in different ways. It also supports a variety of I/O standards and features, so it can connect to different kinds of external devices. The data can go directly from I/O pins to the computation engine and back out after the processing is done, and everything is done in one chip. This is quite different from the other processors. For example, in general purpose processors, you typically have to have an operating system to pull the data into the main memory, and then the processor will access the data at memory and then read data back to memory and then send the data out from I/O device. Whereas in FPGAs, the data I/O and computation engine is so close that there's almost no delay. There are many different FPGA chips. From Altera, it has different families of FPGAs, depends on the chip size, the operating frequency, and it has, for example, Max, Cyclone, Area, Stratix series. Now we understand the basic architectures of FPGA. Now we want to look at the typical programmable logic design flow. Typically, programmers will use some high-level description language to design the functions. And they will start with the design specification and use this high-level language, or RTL, to describe the operations, the functions of the chip. And it can possibly use some other high-level tools to do that. For example, in Quartus tool, you can use SOPC Builder and QSys. Other existing design libraries which has implemented basic functions, for example, memory blocks. And then the developer can use functional simulation tools such as ModelSim to verify the design. But in this stage, only the function is verified. There's no actual delay simulated in this stage. After the design is verified functionally, then the tool can be used to do so-called synthesis. Synthesis essentially to translate the design into the device-specific primitives. So at this stage, the tool will have a knowledge about the device that this design is going to be instantiated on. It will map these specific functions onto the hardware resources available in this particular chip. During this stage, optimization will be applied to meet the required and performance constraint. And the result is a post-synthesis netlist. Once we have the post-synthesis netlist, we will run place and route tools. This tool essentially tries to map the primitives to a specific location inside the chip, also with respect to the area and performance requirements. It will specify the routing resources to be used, and it will try to lay out the different logic elements so that the design constraint can be met. The next stage is the timing analysis, where the tool will verify whether the required performance specification are met, and it will provide static timing analysis results. For example, the longest delay, etc. At the last stage, the developer can take the design and run board level simulation or even load the design onto the actual board to perform the desired function and also to test the results, to verify the results. There are tools such as signal tap can be instantiated together so that the triggers can be fired, and that will help the developers to debug any issues if there is any. Like any FPGA vendors, Intel Altera has its own FPGA design toolset called Quartus. In its Prime version, Quartus Prime has many functionalities that can allow you to design your HDL code, also can allow you to connect your HDL code to existing IP libraries to complete your design. It also has the descriptions of many of the FPGA parts from Altera. Quartus Prime framework is an integrated tool that can support multiple design entries. Once you have the design implemented, you can go through the complete design flow, such as synthesis, place and route, timing and power analysis, and eventually program the binary into an FPGA device. So the bigger question is, why we are doing OpenCL on FPGAs? Think about the programmers community. There are many people who are familiar with CPU programming, using high-level languages C, C++, Java, or even assembly language. There are chip designers who are dedicated to design ASIC chips using low-level tools. And there are a small community of FPGA programmers which can use HDL and also other design tools to describe the functionality of the chip and also to implement the functionality on FPGA. Now, with OpenCL, we have a great opportunity to expand the programming environment that available on the FPGAs to a larger community. With OpenCL, people do not have to know about hardware description language such as Verilog and VHDL. Instead, they can use a more familiar C-like programming language, OpenCL, to write parallel programs. In this way, OpenCL expands the number of application developers. As a result, more applications can be designed and mapped onto FPGAs. OpenCL actually provides an abstraction away from FPGA hardware. Not only the resources on FPGA, but also breaking away from the traditional FPGA design tools, so that we can bring the FPGA to a broader community of software programmers. And these programmers can write, optimize, and debug in a familiar environment that has been widely used in many different platforms. And Quad software and also other FPGA development tools can run behind the scenes. And the tool can also provide an emulation environment and profiler so that the programmers of the OpenCL can run these emulation and profiling tools on top of FPGA, which will help greatly the software development, debugging, and optimization. So we talked about OpenCL in the previous lecture. Now I want to just go over very quickly to review what is OpenCL for the people who have not taken the previous lecture. OpenCL is a software programming model and essentially helps software engineers for designing parallel programs on a large number of different platforms, including CPUs, GPUs, and FPGAs. OpenCL supports heterogeneous computing in the sense that for one OpenCL program, it can run on both the CPU and GPU, or a CPU and FPGA, or even a CPU, GPU, and FPGA altogether within one platform. With OpenCL, it can support many different hardware platforms. It breaks away from the very low-level development environment and tools specifically for FPGAs. It can increase the performance with the hardware acceleration from FPGAs or GPUs. OpenCL standard is open, royalty-free, and has been adopted by many different chip vendors. OpenCL is managed by a group called Kernel Group, and many leading chip vendors are the members of this group, including Intel, now Intel Altera, which was in Altera before, and AMD, Xilinx, NVIDIA, ARM, and IBM, etc. OpenCL has evolved greatly from the past 8-9 years, from 1.0 to now 2.0, although different chip vendors may have different level of support to these different OpenCL versions. The big idea behind OpenCL is about the OpenCL execution model. With OpenCL, it greatly reduces the effort of writing a parallel program which can be executed on multiple processing elements or multiple compute units. Essentially, using OpenCL kernel, you can define an n-dimensional computation domain that can be mapped into multiple hardware units. And each kernel will be executed on this execution unit at certain computation time. Let's look at this example. On the left side, we have a traditional loop, which does the vector multiplication. So the inputs are 2 vectors, and the output is a third vector, and we're taking element-wise multiplication, and we want to put the product into the third vector. So as you can see, there's a lot of parallelism in this traditional vector multiplication operation, because the multiplication on these elements can be performed independently from each other. Now, in order for this kind of highly parallel task to be executed on a parallel hardware architecture, such as GPU or FPGA, you can think of many different ways to instantiate that. Using OpenCL, you can effectively describe the functionality and the parallelism in such functions. For example, we show the kernel that we could design for this vector multiplication on the right side. The inputs are two vectors, and these two vectors, A and B, are stored in a global memory. That's why we have a keyword global. And the output of this function, of this kernel, is another vector called C, which is also stored in the global memory. Now, what we see here is in this kernel function, we will first get the global ID of this work item. Now, we break down the whole multiplication process into multiplication on individual element in the array. So each of the kernel is actually doing one multiplication operation on one of the elements from A and B and put that product into the corresponding element of C. So what you see here is once we get the global ID or the identifier of the work item, we will use that as an index to find the corresponding element in vector A and B, and we perform the multiplication operation, and the result will be put into C and the same location as we have using the index ID. Now you may wonder, you are doing only one multiplication on one of the elements in the vectors. Now what about the rest of the elements? What we don't see in this example is that OpenCL actually handles the parallelism very nicely. So in the main program that launches this kernel, what we are actually going to do is we're going to say we're going to run this kernel on a one-dimensional computation domain, and we're going to have a large number of kernels that are being launched and executed on those computation units. So even though within one single kernel you are seeing here only one multiplication is performed, but in fact we have multiple kernels that will be executed altogether on this parallel hardware. Now we're taking a different view of this kernel-based OpenCL programming. So what we see here is not only the accelerator, in our case the FPGA, which has global memory and local memory, and also we're going to have the kernels instantiated on the multiple computer units. In addition to that, we have the host side processor and also the host side program. On the host, the main program actually prepares the data for input and for output. It does typically buffer allocations. Also, it will handle the OpenCL context, and also it will handle those OpenCL buffer operations. We see here this CL in-queue write buffer, which is typically used for moving the data or copying the data from host memory to the device memory to get it ready for the kernel execution. And after the kernel is completed, correspondingly, we will have this CL in-queue read buffer to read the results from the device memory to the host memory, and so that we can display the result or do other things. Now, in between write buffer and read buffer, typically we will have this kernel launch. And to be more specific, we have here CL in-queue ND range kernel. ND range kernel really means that n-dimensional kernel, that we're going to launch a kernel named sum, or a vector multiplication in the previous case, and we're going to say how many kernels we want to launch and what are the parameters that we're going to give to this kernel function. And in this example, we have a simpler kernel function. It's called summation. So what we do here is very similar to what we did in the vector multiplication. So we'll get this ID index by using global ID of the kernel function, and we're gonna do the addition of the one element of A and with one element of B using the index, and we're gonna store the result into Y, which is the output parameter of this kernel function. So this diagram shows you that Now, what we're going to have on the host side and to prepare for the kernel launch, and what do we have on the kernel. As we already know that this kernel will be executed on this accelerator, either a GPU or FPGA, and we also know that there will be multiple kernels being executed at the same time because of the available compute units and because the way we launch these kernels. The program on the OpenCL host is really a C or C++ pure software program. It's a serial program. There's no really parallelism on the host side software. The communication between the accelerator device and the host is handled by using these in-queue buffer operations. Now, we mentioned earlier that we have this CL in-queue write buffer. This is typically used to copy data from the host to FPGAs. And on the other hand, we have this CL in-queue read buffer to copy data, the results, from FPGA back to the host. And this CL in-queue and derange kernel is where we ask the FPGA to run the kernel, and also we define how many kernels we want it to be executed. OpenCL kernels are essentially data parallel functions. It defines that what the compute units should be doing within one single kernel. So even though you don't see that a single kernel is going to perform the operations on the complete array of your data or complete set of the data, but in fact, because the kernel is being executed as multiple copies, multiple instances, so that's how the complete data set is covered. Each of the kernel defines many parallel threads of execution, and each thread can use this get global ID to get its own identifier, which can often be used as an index to the data set. It also contains kernel extensions to specify parallelism and memory hierarchy. For example, in this case, we want to say that this vector A, B, and answer are all global memory vectors or global memory buffers. And the kernel can be then executed by different compute units, for example, CPUs and GPUs and FPGAs. In order to differentiate the kernel instances, the kernel function often use global ID or local ID to find some kind of identifier so that these ID can be used to determine which slice of data the kernel should be working on. And threads are organized into work groups, and the threads within one work group can share local memory. So there are differences between threads within one work group and across work groups, because for threads across a work group, they cannot share the local memory data. In this example, we show that here we have 3 work groups, and in each work group, we have 5 threads that are performing some kind of kernel function. And with the built-in functions related to identifiers, we can find the identifier of these threads. Get group ID will return the group ID of the thread. In this example, if this thread is calling get group ID, it will return 0, and if this thread is calling get group ID, it will return 2. Local ID is the identifier of the work item within a group. So in this case, the local ID will be from 0 to 4, and same case in this work group, the local ID will be from 0 to 4. Global ID can actually be calculated by using group ID and local ID. Once we know the group size, we can use the group ID, multiply with the group size or the local size, and then plus the local ID, and that will give us the global ID of that thread. We talk about memory on the FPGAs and also on other processors that support OpenCL. Essentially, we divide the memory into private memory, local memory, global memory, which often consists of constant memory, and then host memory. Host memory is memory on the host side. So the DRAM, the main memory, is the host memory on the CPU side. On the device side, it often has a large amount of memory on the acceleration card, being either FPGA or GPU. And this is the global memory, which is shared by all the compute units available on this hardware accelerator. Inside the global memory, we often have a small region that stores the constant numbers, and that can be read by all the threads on the processing elements. Within the kernel, we differentiate local memory and private memory. Local memory, as we mentioned earlier, that these different work items can share data through the global memory, which is specific to a work group. For each work item or for each work thread, it has its own private memory that cannot be visible to other work items, even in the same work group. And of course, the size and speed of these memory components are different. Private memory is the closest to the execution unit, so it has the fastest speed, but size-wise it's very small. Local memory is a little bit larger, but the access speed is slower than private memory. And for global memory, the access speed is even slower, but the size can be very big. Now, once we have the host side program and the kernel program, we can compile this whole application and run it on the FPGAs. This is where the vendor SDK comes into play. From Intel Altera, it has an OpenCL SDK, which is a licensed software toolkit. Once you have it installed in your development machine, you can compile the host program and kernel program and run the binary on this heterogeneous architecture. So when you compile a host program, the binary is designed for the host, which is typically a x86 or an ARM architecture. The kernel program is compiled into eventually a binary, and that can be loaded onto the FPGA. Now, this picture shows a little bit more detail about this OpenCL design flow on FPGA platform. We have a host side program called myhost.c. This can typically go to a C or C++ compiler to generate the executable. In order for this host program to work with the kernels, it has to be linked into this OpenCL runtime library that's provided by Altera. And this is in a binary format. You don't really get the source code of this binary. On the kernel side, this .cl is a kernel program. You can use Altera's OpenCL compiler, which is called AOC, to compile the kernel.cl file into HDL program. You can actually see the OpenCL. You can actually see the HDL programs generated by AOC compiler. This hardware description language will be fed into Quartus Prime design toolset, which will go through the typical FPGA development workflow, including synthesis, place and route, all these steps, and eventually generate a bit stream. During this Quartus compilation process, of course, you need to supply the board description so that it knows how to map the binary onto this board. After the OpenCL SDK completes the whole workflow, you will have binary compiled for the host side. Also, you will have the binary compiled for the FPGA. On the host side, on the host side, and now we're ready to execute this binary. On the host side, you actually need the runtime environment provided by the vendor, which includes the drivers for the operating system and low-level abstractions of the hardware, and also the OpenCL API implementation library, so such as the CL enqueue buffer functions. On the FPGA side, as you can see, in order for this FPGA to talk to the processor, you actually have to have a little bit more than just the kernel function you write. You have to have the interface controllers, in our case the PCIe controller. You need to have memory controllers to talk to the external memory, which is in fact the global memory. And you may have other things that you want to talk to. All these components are provided as part of the board support package. So you need to have the vendors provide such components so that the OpenCL kernel generated can communicate with the processor and with the memory components outside the FPGA. Now everything here is in fact generated by the user kernel, which can include the kernel data path, some on-chip memory, and also local memory interconnect. For talking to the global memory space, it has to go through this global interconnect, which in turn talks to the memory controllers or even the PCIe controllers so that it can talk to the host program running on the processor.